Thank you, Laurent. So first, I thank the organizer to invite me. For more than 25 years, I work with people from tectonics and paleomagnetism, but I think there is some room for improvement for myself. And so it was a real pleasure to be here and to learn a little bit about the interior of the Earth and processes governing this. Now we will get out a little bit for the last half an hour to breathe outside from the interior of the Earth, and I will talk to you about climate and the link between tectonics and climate. First, I have to thank also a lot of engineers at developing numerical code for climate that I'm using, and I will show you that, and also a bunch of workers and colleagues, and also PhD that has worked for me and with me these last 25 years. So before going inside the topics, the next slide show you I got a little bit deeper than 68. A little bit deeper because I think it's important for us to think about what was the science 1 century ago before the establishment of the tectonics as an engine to understand really what was going on. And so a very important piece of work had been done by Wegener. And Wegener, you know, he published his first papers in 1912 and then his first book in 1915. But in the framework of this talk, the most important thing is maybe the paper he made with Koppen. Wegener and Koppen, they were really large and very open-minded scientists, both of them, especially Koppen, but Koppen lived twice as long as Wegener, nearly. Koppen was a guy that was able to do methodology, climatology, and biology. Until today, we are using the classification of Koppen for different kind of biomes. So both together, they published this paper in 1924, and this paper was on the impact of continental drift on changes of continent, climate over this continent, precipitation, temperature, and at least vegetation. Something was missing, and this is the next slide, in this beautiful explanation of the first direct link between tectonics and climate. And this is the guy that I want to introduce now, which is James Walker. James Walker is certainly one of the guys that first thought that there is an important link and an indirect link between the continental drift and the climate, which is CO2. We get for those that was already here, and I hope most of you were, we got a beautiful seminar by Dietmar just before the break, the lunch. And so you know that the idea of Walker was that there is in fact an equilibrium of the CO2 in the atmosphere, which is driven, it's very, 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 very simple, which is driven by the fact that you enter CO2 in the atmosphere by the volcanism, and you get out the CO2 from the atmosphere mostly by silicate weathering. I am very, very simple. And between this sink, this source, and this sink, the fact that the silicate weathering occurs on continent depends drastically on the location of this continent. So I showed just at the bottom of this slide 3 configurations. One, I will talk about it. It's a configuration of the last supercontinent, the last supercontinent, the Rodinia, 805,000 million of years before present, and another configuration and present day. If you think about it, there is an indirect link between climate and plate tectonic, which is linked to the fact that the continental plates will be in the tropic, the most there will be rain, they will be eroded, and as Dieter explained, the CO2 will go from the continental plates to the bottom of the ocean. And it's the reverse if these continental plates are at high latitude where it's really dry. So Walker gets this idea, and this idea is fundamental to understand the regulation at long terms of our planet. Why we are here. Why the planet has always, most of the time, I will talk about that a little bit later, been regulated at temperature and hydrological cycle consistent with life. This is only one of the explanation. So, okay, this talk will be devoted to some, because there are many, many, illustration of the link between tectonics, climate, and CO2. So I will first show a crucial, pivotal, and very simple link between the configuration of the continents and the climate, and this is how you get in a snowball. Why? At Neoproterozoic, you get a deregulation of the climate system who may have led to a complete snowballers. This is really seriously linked with the configuration of the continents. And then I will show you two other illustrations. One is linked to the fact that with tectonics, you also make disappear epicontinental sea, and this is a case for Tethys. Yesterday we got some information on that. And so I will talk about the impact of the disappearance of this large sea from 40 million years ago to present day on both systems, Asian monsoon system and African monsoon system. And the last illustration of my talk will be on the fact that tectonics makes appear also large mountain ranges that change not only the atmosphere, but I will show you an example on ocean dynamics. Okay, so I will go briefly on this next slide. This next slide is exactly what Dietmar explained. This is the exospheric cycle of CO2. So when it rains, the droplet take into the liquid a little of CO2 and acidify, and then there are reaction on and silicate weathering, and this silicate weathering makes the reactions that are shown here makes the possibility to extract one CO2 molecule from the atmosphere and to drive them through different kind of carbon reaction at the top of the ocean, and then to sink in the bottom of the ocean, and then by subduction to be again in the mantle and again volcanism. This is a long-term cycle of the carbon, and this is really something which is at least very specific for the Earth, and we have to know because this is one of the elements that regulate the climate at long time scale. So the next slide is showing you what happens, because as you know, the sun is increasing by 7% by billion of years. So at Neoproterozoic, about 700 million of years ago, the sun was already 94% of what it is now. So the fact that at this luminosity an accident occurred was mysterious at the end of the last century. And there were many proxies that show that during Neoproterozoic something strange happened. And I will try to convince you that one reason to get into this kind of accident is purely linked to the configuration of the continent. So this slide shows you that about 1,800,000,000 years ago, we get a big supercontinent called Rodinia that was centered on the equator. Okay, as Dietmar said, the reconstruction with biomagnetism and other proxies of this continent is far to be as good as, for instance, the reconstruction of Cretaceous, the reconstruction that Dietmar can provide for the last 200 million years. But still, we know that it was a supercontinent and it was located in a tropical area. Moreover, when it breaks, a lot of traps occurs, and due to the basalt that recover a lot of the surface, an increased weathering occurs. So the next slide is this question: is it possible to deregulate for only some million of years? This is another seminar, but we can explain the snowballers, why it comes and why it disappears and why it lasts. It can only last on Earth some million of years. And the question is, why at this peculiar moment? And so I will show you using model. So the next slide shows you a little bit of the model. For 30 minutes, I don't talk too much about the model, but we developed a model which is the coupling between a model of intermediate complexity, a climate model, and a model of the carbon cycle at long terms developed by Yves Goderis. And we couple these two models, and we make simulation of the climate and CO2 for the period 800 million years. So it is very crude and simple, but you can see that 800 million years are what the climate has simulated by our models. So our models just account for the fact that the solar was 95% of today. It computes by itself the CO2 in equilibrium with the configuration that we have. And what you can see on this plot here, it is that 800 million years ago, the global temperature was not drastically different from today. What was really drastically different is that we do not have ice sheets, neither in the north nor in the south. By the way, it's very infrequent to have, as today, two ice sheets on the Earth. So, and you see that the temperature were mostly high. So this is okay. Now, what happens 50 million years after? The thing really peculiar for the Neoproterozoic period is that the big supercontinent breaks up in the tropical band. And if you have a continental supercontinent that breaks up in the tropical, it's really the most optimum location to decrease the CO2, because when you get a big continent in the tropics, the center of the continent is anyway very dry, and only the border of the continent are very wet. So the erosion is not optimized. But when the continent breaks, and if it breaks with all the little plates in the equatorial band, you are in a context, in a framework, in a geological framework where you increase the CO2 trapping and you decrease the CO2. And this is one explanation. There are several explanations. I'm a little bit simplistic because I want to show you many illustrations of the capability we have linking tectonics and climate. But this is a powerful explanation that we published a long time ago. Now that's never been, there is no contradiction with that. The next slide shows the decrease of the CO2 provided by this peculiar configuration of the breakup of the Rodinia. So this is a first example, and I will try to show you some more examples in another context. And first, I want to show you a kind of movie that we have done with Jean Bess from the IPG at the end of the last century. So I think that in a few years, Dietmar Müller will be able to make better cartoons. So what you see here is a dislocation of the Pangaea from 250 million years, as seen for the models. So when you look to that, you see many things. In fact, you see that the continent is breaking. You can also see that about 100 million of years ago, the Antarctic was already in a polar location. But as you know, the Antarctic ice cap only comes 34 million of years before present. That means that during more than 60 million of years, the Antarctica was free of ice. Why was it? The reason was explained by Dietmar this morning, because the last 40 million years, the CO2 always decreases from Eocene to present day by about a factor of 4. So it's only 34 million years ago when a threshold was then in the radiative forcing that an ice cap can be installed over Greenland. You can also see on this movie the Indian plate that leaves Madagascar and make a collision that will lead to the Tibetan Plateau. I will talk also about that. So I think it's a really kind of primitive movie. On this movie, there are many things that are lacking. The first and important thing is that it's a 2D movie. So what about the third dimension? I will come back also to that. The third dimension, a proxy for the history of elevation of mountain range, is really, really a difficult task. So we are a little blind on that. We know we are able, thanks to you, to have information on the plate distribution, but on the elevation of the mountain range, it's really a difficult question. Now, compared to Wegener and Koppen, they show the vegetation. We could do that. There are a coupling between vegetation model and climate model. There are plenty of things that we can do with a coupling, and here on this movie, you only see the change of continent, the topography, and the change of bathymetry, and the change of seaway, for instance. You see the Tasmanian, you see the Drake passage, you see all these passages that will change the ocean circulation. Okay, so now I will go to the second point of my talk, which is mostly devoted to a study that we have made about 20 years ago, and that we have renewed about 5 years ago with other colleagues. So this here is a paleogeography of the global Earth, because we get global models that are working on the whole globe. So we prescribe boundary conditions to try to infer how the energy of the two fluids, the atmosphere and the ocean, share and bring the energy from the equator to the pole. And for that, we need the paleogeography. So on this plot, you saw the paleogeography as it was 30 million years ago. No, as it is put in the boundary condition of the model with the spatial resolution we have. So here it's a general circulation of climate, so it's a better model than the one on the snowballers, a very good model, in fact. And this shows you the boundary condition we use for this shrinkage of the thetis. And at this time, at the end of the 90s, the major idea was to look to the effect of these changes on the Andean monsoon. Because at this time, Rudiman and Rhine and many American have shown that the uplift of the Tibetan Plateau drives the monsoon. But I have to say that when I went to the IPG, I met two very good scientists, dead now, but Marco and Riku, and they told me, hey, Gilles, it's not only the uplift of the rift, there is a large and huge epicontinental sea that shrink. And so Frederick and I and Jean, we make this simulation with a model to quantify the impact of the disappearance of this epicontinental sea. And the next slide shows something that you can imagine only being sat on your chair. You don't need a model for that. It is that when the sea has disappeared and completely shrinked, and now the remainder of the sea is just the Mediterranean, the Caspian, and some reminder like that, it's a very, very, very small. When it disappeared, of course, the summer were hotter and the winter colder, because you replace a big sea by a continent. So this increased considerably the monsoon transport, and this monsoon transport break the zonal circulation that was before. That means from the last 40 million of years was a time of increased monsoon. And what is really incredible with the model, and this is the next slide, is the fact that the model, it's several lives. That means that you can, with your model, quantify the sensitivity of the climate to different things. So on the first plot, what you see, it is a June, July, August precipitation. And you see that in anomaly, that in difference between a climate where you have a big Tethys Sea, as it was 30 million years ago, and when you remove it. And this is a difference in terms of summer precipitation. And the bottom plot shows you the same thing, but removing the Tibetan Plateau. And as you see, in fact, of course, the Tethys was very big, so it has a very big effect at regional scale, whereas the Tibetan Plateau has also an important impact, but more localized. Okay, so this was done maybe 20 years ago with Fred and Jean, and maybe 7 years ago, I received a paper from a Norwegian guy, which is also Chinese, and he did the same thing than me, and this is the same shrinkage of the Paratethys, but he was more clever, in fact. He thought, what about the African monsoon system? What about the changes in Africa during that period? So we redo this experiment, and we get results that are more important for me, because at the end of the shrinkage, it is the Tortonian, 7 million of years, and this is the origin of Tumai, and this is the climate in which our ancestors really live. And what we find, and this is the next slide, it's on the precipitation, and what you see here, it is a precipitation average on the Sahara during this shrinkage. And the bar graph you see is the fact that there is a shift, and of course the shrinkage acts also on the monsoon. There is a shift on the monsoon, and this shift produces the onset of the Sahara. And this is in good agreement with the fact that about Tortonian, the Sahara existed as a desert with some modulation, as you know, due to the precession cycle, but really emerged as a desert about Tortonian. So this is really linked to the shrinkage of the Tethys. But more importantly, and this is the next slide, in a context where you get a large Tethys, and in a context where you don't have this large Tethys as today, the modulation of the cycle of the monsoon is drastically different. So the precession, which is a driver of big monsoon and small monsoon, is amplified when there is no more Tethys. And this picture shows you that the response of the Earth to orbital forcing is much enhanced. And this is very important because during Tortonian, if you look to the fossil, you will see that most of our ancestors are east side of the rift, and only a few are west side of the rift. And this can be explained by the fact that there were intensified monsoon, and from time to time, it was just possible to go to the Chad Lake. So we can understand a lot of things about the dispersal of our ancestors by climate and tectonics. Okay, so now I finished with the shrinkage of the paradiddles, and I go to the last example, the last illustration I want to show you, which is quite interesting too. This is a paper published in Nature some years ago, that kind of study that we can do, which disentangle the fact that when you get the uplift of the Tibetan Plateau, you get two different forcings, which are in the real life completely associated, but you can disentangle by model. One is the fact that you get a mountain range, which will change the atmospheric circulation for sure. And the other one is that the albedo, that means the capability to reflect the light, is also changed because you get also snow. And here you can see the result of this guy. That they show that between these two effects, the most important is indeed the uplift of the rift. Okay, but as I told you before, and as I will tell again and again, the paleo elevation is one of the most difficult things to reconstruct in time. So now I will show you two other illustrations. One, this is the next slide, is only to do, has been published last year, and it's a very simple, not so simple, but very simple idea. When the collision took place between the Indian plates and Asian continent, where was India? India was really at the tropics, in the tropics. And where is Himalaya and Tibetan Plateau now? They are in the subtropics. So to try to understand the impact of this thousands of kilometers of northward shift of the Tibetan Plateau and Himalaya inside the Asian continent, we make two experiments only with an atmosphere general circulation model. And so we get a quite fast response. We prescribe the bathymetry, we prescribe the sea surface temperature as we get it from the reconstruction. And what we did, we changed the location, just the location of the Tibetan Plateau and Himalaya from, let's say, 10 to 12 degrees north, where the collision occurred, to the present location. And the next slide shows you what happened then. Of course, depending if your mountain range is or not in the tropic, the impact on monsoon is drastically different. So because I have too much time, I don't show you the result in terms of atmosphere, wind stress, and sea level pressure, but I show you just this very simple scheme that shows you that if you interact with the monsoon in the tropical area, the impact will be much weaker than in the subtropic. And to convince you that this simulation has some relationship with reality, I show you a plot a bit complex where you can see the monsoon region and the monsoon domain. On the top plot, you can see modern configuration of the monsoon with the Tibetan Plateau in subtropics. And at the bottom and right, to go faster, you can see the situation 40 million years ago with no Himalaya and with the Tibetan Plateau, which is located 11 degrees north. And as you can see here, the impact on monsoon is much weaker. And if you look to the data, you see that indeed, during all these periods, you get an intensification of the monsoon, and also the fact that the Chinese inner desert developed during that period. And we can show that with our simulation. Now I will show you another example which is not really straightforward, and this is why I want to show you this. What happens if we remove the Tibetan Plateau from the oceanic circulation? This is the next slide. During all these years, this last, let's say, 30 years, a lot of groups make sensitivity experiments of Tibetan Plateau and Himalaya. They don't know how much was the Himalayan Tibetan Plateau in the past, and especially during Miocene, but they did experiments of sensitivity, okay, no problem. And they look only the atmosphere circulation. Here, we make an experiment where we do both, with TP and without TP, and we make an experiment with atmosphere and ocean. And what I show you here is the condition of the experiment. We just remove the Tibetan Plateau. But these experiments last for long. So you see the first 1,000 years, it is to mimic present day, and we mimic it quite well. And the last 2,000 years is to mimic what happened in the atmosphere-ocean system when you remove the TP. And you see on the plot that shows the temperature of the surface and the temperature in the deep ocean 1,000 meters deep, that, okay, we get equilibrium for both simulation, and by the way, you can see that the temperature and the temperature below 1,000 meters for present day are totally correct, and you can also see how the ocean works, and it doesn't work exactly the same than today. When you get no TP, instead to have a strong Atlantic meridional circulation as today, and in the present day simulation we get the good value for the AMOX, Atlantic meridional ocean circulation. That means the energy that goes from the Atlantic, from the equator to the pole. So it is about 15 sphere drop for today. When you remove the Tibetan Plateau, you decrease considerably this transport, but you increase the Pacific one. So what does that mean? That means that, in fact, when you remove a mountain range as the Tibetan Plateau and Himalaya, you not only change the pathway of the air mass, you also change the wind, you also change the runoff, you also change the water cycle and the salinity of the ocean, and at the end, you change the transport of energy by the ocean. So the next slide shows you what we call the stream function. It's something that we use a lot in ocean dynamics, and this is for the Atlantic meridional ocean circulation with TP and without TP, and bottom it's a Pacific meridional ocean circulation, and you see exactly what I told you. That means that when you get no TP, you seriously decrease the AMOC. So the mountain range has a major effect on the ocean circulation. The next slide is just to tell you that I say that very simply because I'm summarizing, but in fact there are many, many feedbacks in the system, in the climate system, that may explain this result. It's not at all straightforward. We have really to analyze it, and for instance, to get this result, we have to understand the change of sea ice, many, many things I have no time to discuss. But what you have to remind is that when you remove a big mountain range, you change completely not only the atmospheric circulation, but also the ocean circulation. Now I'm going to the last illustration. I told you about the Tibetan Plateau and Himalaya, and now I go also from India to Africa, and I'm not showing you the beautiful African rift. So Pierre and I, when we want to simulate the effect of the African uplift, it was really too difficult. We discussed with people with geologists, and to get, as I told you, an history of the elevation of the African rift through time during this last 30 or 40 million of years, it was just too complex. So in the next slide, show you how we are only modelers. So what in fact interests the modelers is to make sensitivity experiments, to understand how the climate works and what was the climate before the rift. So we made 3 sensitivity experiments, one without rift, no rift, one with a present-day rift, and one accounting for the traps and a kind of mid-rift. With these 3 experiments, I just summarize you the results to show you that indeed it changed a lot, and it changed also for the environment of our ancestors. Because at the end of the uplift of the rift, 3 million years ago, now you get on this slide the changes in precipitation. So what you see here is the rainfall simulated by our model when we have rift or no rift. When we have no rift, no African rift, the African monsoon enters into the eastern Africa and is able to wet, and this is the reason why you get a lot of forest till 3 million years ago over the eastern Africa, and then you get an aridification of eastern Africa. And so this is what we see in our simulation. We see that when the rift is uplifted, we get more and more dry and arid vegetation. And the next slide shows you what we get when we couple our climate results with vegetation model. And you see that we are transforming the vegetation from arboreal forest to herbaceous forest. And this, okay, and I'm finished. And this change is maybe the oldest of you know this story of Koppen's called the East Side Story. And this is a quantification, in fact, of this, the fact that our ancestors, they get from an arboreal environment with many forests to forests that reduce, become more or less mosaic, and then herbaceous, and they have to adapt to that, and certainly to reinvent the bipedi, because the bipedi was already there when in the time of Toomai, so it's just a reinvention. But they have to adapt to this major climate change, and this climate change is first driven by the uplift of the rift. Okay, so now it's the end of the journey. I try to convince you that there are many illustrations of the link between what you are doing from the interior of the Earth and what we are doing with your boundary condition at the exterior of the Earth. So what's next? This is a joke, in fact. This is another movie that Jean Bess gave me, and it's just to show that we can make some approximation. We can imagine what will be the plate tectonics in 10, 20, 30 million years with some approximation. And what I told you about the link between the CO2, erosion, climate change will remain, of course, true. So we can say something about what will happen in the CO2 and climate due to the tectonics in the future, of course, because we have done it for the past and for longer. So it is possible. And another thing, which is just to finish with, is that what we cannot know is the link between the CO2 and the climate change, because we are producing such big variation in a very small time step of 200 years of the CO2 in our atmosphere, that this will, not for tectonics long term, but for human, being a real challenge. So the last slide is for acknowledgement to the different founding system I got, and also a little sentence to say that I think I convinced you that there are many targets, many challenges, a lot of good science to do between interior and outside from there, and the exterior, external atmosphere and ocean changes, and that for that we need to host students for a long time. And short-term fundings and jobs, I think, endanger our fundamental research system. And I will finish like this. Thank you.